Dear students, let me welcome you all to a new edition of physics. In this edition, we'll revise the first 3 chapters of the curriculum. You will be encountered with miscellaneous questions. Questions such as what happens when, write the scientific term, write the relation, give reason, choose. Also, we'll be able to solve some problems. So let's get started. Revision on the first 3 chapters. Yes, what happens when? First type of questions. What happens when? Okay, in front of you we've got a circuit, and we want you to explain what happens when the switch K is opened. Okay, thank you very much. And you have to account for your answer. The lamp momentarily flashes due to, because of the high forward EMF induced by self-induction. What happens when the 2 metallic rings in an AC dynamo are replaced with a split cylinder commutator? The 2 rings are replaced with a commutator. Okay. The AC current becomes unidirectional, but varying current. Once again, the AC current, as shown in front of you, becomes unidirectional. Unidirection has one direction, but still changing. It swings from 0 to maximum. In front of you, what happens when the value of R1 is decreased with respect to the readings on the voltmeters? As a matter of fact, we've got 2 voltmeters. Voltmeter 1 located, yes, across the 2 terminals of the battery, and it measures terminal voltage. V2 measures the voltage across R2. And value of R1, yes, was decreased. V1 decreases, but V2 increases. We'll explain this. When R1 is decreased, total resistance of the circuit decreases. Current through the battery increases. When current increases, lost voltage or internal voltage increases, so terminal voltage decreases. But what about V2? V2 is given by the product of the current and R2. R2 is constant, so it depends on the current. When R1 decreases, current increases, so V2 increases. Once again, decreasing the value of the variable resistance decreases the total resistance of the circuit. When R1, yes, is decreased, R total is decreased. And current passing through the battery means current increases. And this causes the internal voltage to increase. And when internal voltage increases, terminal voltage decreases. V2 increases because it is simply proportional to the current. Another type of questions: when does each of the following quantities equal 0? Torque acting on a coil carrying an electric current and placed in a uniform magnetic field. So we've got a coil carrying current and it is placed in a magnetic field, but torque acting on it is 0. Yes, this happens in the vertical position. The torque equals 0 in the vertical position, where plane of the coil is perpendicular to the magnetic field. Expression that gives torque, yes, it is BIA and cosine theta. Theta is the angle between plane and field, and it is 90. Okay, when theta equals 90, cosine 90 equals 0, so torque equals 0. When does the EMF induced in a wire moving in a uniform magnetic field equal 0? So we've got a wire, and the wire is moved in a magnetic field, but no EMF is induced. Actually, it happens when the wire is moved parallel to the field. The wire is moved parallel to the field. The expression that gives the EMF induced, EMF is equal to BLV sine theta. B, magnetic flux density. L, length of the wire. V, linear velocity. Theta is the direction between motion of the wire and field. If it is moved parallel, EMF is then equal to 0 because theta is 0 and sine 0 equals 0. And don't ever forget, theta is the angle between the field and direction of motion of the wire. When does the force of a magnetic field on a current carrying wire equal 0? Force of a magnetic field. Let me explain this. We've got a wire and a current is passed through the wire, and the wire is placed in a magnetic field, but no magnetic force acts on it. Yes, thank you very much. The wire is placed parallel to the field. When the wire is placed parallel to the field, force is given from the expression BIL sine theta. Force equals 0 when theta equals 0. Okay. When does the instantaneous EMF induced in a coil rotating in a magnetic field equal 0? Coil of the dynamo, we want you to tell when exactly EMF is equal to 0. Does it happen in the horizontal position or vertical position? Instantaneous EMF induced equals 0 in the vertical position, where the plane of the coil is perpendicular to the magnetic field. Okay, but sides of the coil, limbs of the coil, yes, moves parallel to the field, so no cutting, so no EMF is induced. EMF instantaneous equals EMF maximum cosine alpha. So EMF instantaneous equals 0 when alpha equals 90, cosine 90 equals 0. Alpha is the angle between plane of coil and magnetic field. When does the current, we've got current that flows through the primary coil, and the primary coil is connected to the mains, but no current passes through it. Yes, this happens when the secondary coil, yes, or secondary circuit is unloaded, is open. That's to say when the secondary circuit is open. And now we've got a problem. The figure shows two long straight wires that carry the same current, I1, but in opposite directions, and a loop that carries current I2. Okay, when we've got two wires carrying currents in opposite direction, the field inside the two wires, in between the two wires, will have the same direction. Okay, so the two fields of the wires, yes, in between the two wires will have the same direction. Okay. When a compass is placed at the center of the circular loop, it shows no deflection. We want you to compare I1 to I2. Okay? Compass shows no deflection means the two fields or fields cancel out. We've got three fields. Fields of the wire, which have the same direction, must cancel the field of the loop. So we can say at the center, the two fields of the two straight wires to be wire, yes, equal and opposite the field of the circular loop. So 2 times mu I1 over 2 pi r. Your attention here, it should be written d, but at the center, the distance is equal to the radius. Is equal to, yes, field of the circular loop, permeability in I2 over 2r. Number of turns here is 1. Okay, permeability will be cancelled out. and 2. Also radius will be cancelled out. Okay, so we can say 2I1 over pi is equal to I2. So I1 over I2 is equal to pi over 2. Another problem. Now we've got two wires, two straight wires, one carrying current of 20 amperes, the other carries current of 15 ampere. And we've got a circular loop, okay, and you pay attention to the distances. Distance between the two wires is 40 centimeters. By the way, two wires carry currents in the same direction, and this means that their fields are in opposite direction in between the two wires, okay? The figure shows two long current carrying straight wires. The two wires are 40 centimeters apart. The first carries a current of 15, the other carries a current of 20. A circular loop or coil of radius 2 pi centimeter, a circular coil of radius 2 pi centimeter is placed between the wires such that they all have the same plane. If the current flowing in the circular coil is 0.05 ampere, current in the circular coil is given 0.05 ampere, and magnetic flux density at the center is 0. Total magnetic at the center is 0. We want you to calculate the number of turns on the coil. We want you to calculate number of turns on the coil. Okay, so B circular plus B wire, yes, B circular plus magnetic field of wire B, they have the same direction and they are opposite to the field of wire A. Okay. Once again, let me explain it. We've got two wires carrying current in the same direction. So the field between them, yes, in opposite directions. Okay? So one of them, the field of wire B, is added to the field of the circular coil. And these two fields are cancelled out by the field of the other wire, wire A. So we can say mu 0.05 over 2 times 2 pi times 10 power negative 2. So we can say 0.05 over 2 times 2 pi times 10 power negative 2 times permeability, of course. This is the field of the circular coil plus the field of the wire that carries 15 current ampere over 2 pi times 0.2 equals permeability 20 over 2 pi times 0.2. So we rearrange this. Permeability times 20 over 2 pi times 0.2 minus permeability 15 over 2 pi times 0.2 is equal to permeability of, this is of the circular times 0.05n over 2, okay, times 2 pi times 2, 10 to the power of negative 2. So permeability will be cancelled out and number of turns will be 10. Okay. Another type of questions. We've got two circuits here, circuit A or coil A and coil B. Coil B contains a bulb and a battery, and direction of the current is shown in front of you. And the question asks for what happens to the brightness of the bulb in the instant that coil A is pulled away from coil B. Okay, will the brightness increases, decreases, or unchanged? So coil A is moved away from coil B. When this coil is moved away, this will induce an EMF. If the current induced in coil B is in the same direction of the current of the battery, brightness will be increased. Okay? So brightness of the lamp increases. Why? Because the forward EMF induced in coil B by mutual induction, okay, when the coil is being pulled away, is in the same direction of the battery current. So the lamp brightness of the lamp increases. And now we've got two wires carrying currents. One of them carry a current of 1 ampere. The other carries a current of 2 amperes. And they are placed, yes, mutually perpendicular. We want you to calculate total magnetic flux at point Q, which is 20 centimeter from wire X and 10 centimeter from wire Y. So calculate the total magnetic flux at point Q. Magnetic flux density due to wire X at point Q equals 2 times 10 to the power of negative 7. Current through the wire X, which is 2 amperes, over distance, which is 20 centimeter, 20 times 10 power negative 2, to convert it into meter. So it is equal to 2 times 10 power negative 6 Tesla. We'll do the same concerning magnetic flux, but due to wire Y. Magnetic flux due to wire Y equals 2 times 10 power negative 7. Current through wire Y is 1 ampere, distance 10 centimeter. So it is 10 times 10 power negative 2. And it is also equal to 2 times 10 power negative 6. Okay? When we determine directions of the two fields at point Q, they are in opposite direction. And they are equal, so they cancel out. So total magnetic flux will be 2 times 10 power negative 6 minus 2 times 10 power negative 6, it is 0. Now we've got another type of question. We've got a diagram, and a student disconnects the voltmeter shown in the diagram, in the circuit. Okay, and connects in its place a battery and a switch. So the voltmeter is replaced by a battery and a switch. And this, yes, will convert the device into a motor. But when he closes the switch, the coil does not rotate as it should in a DC motor. What is the reason for this? And what other change will he have to make before the motor works properly? Okay, there is something wrong here. The coil will not rotate in one direction. You know why? Because of the presence of two rings. Because of the presence of the two rings. The coil reverses the direction of rotation twice a cycle. Each half cycle, it reverses direction of motion. So, to change this, to correct this, the two rings should be replaced by a split ring commutator. Okay. What is the function of this commutator in the motor? Actually, it reverses the direction of the current in the coil each half cycle to make the coil rotate in one direction. It reverses direction of the current twice a cycle. In this way, the coil can rotate in one direction. We've got a problem, a circular coil of 20 turns, each of radius 4 centimeters. So number of turns is 20, radius 4 centimeters. Resistance of the coil is 2 ohm. Is placed at the center of a larger circular coil of radius 50 centimeters. And number of turns on the larger is 10. And it carries a current of 8 ampere in the clockwise manner or clockwise direction. If the two coils have the same plane, and the current in the larger coil falls to 0 in 1 microsecond, calculate the value of the current induced in the smaller coil and its direction. We need to calculate magnetic flux density at the center of the large coil. It is permeability, which is 4 pi times 10 power negative 7 Ni over 2R. So 4 pi times 10 power negative 7, number of turns is 10, current 8, and radius is 50. So 2 times 50 times 10 power negative 2. This is the field density at its center. It is equal to 10 to the power of negative 4 Tesla. EMF induced in the smaller coil is equal to, yes, Faraday's law, negative N, negative sign here indicates Lenz's rule, delta phi magnetic over delta T. We can write it N AB over delta T. So it is equal to 20. Okay, area pi r squared, so pi 4 times 10 power negative 2 all squared times magnetic flux density. We managed to calculate it, 10 power negative 4, and time is given 1 microsecond. So 1 times 10 power negative 6, EMF will be 10 volts. Okay, if you want the current, it's all easy. Current is given by EMF over resistance. So it is equal to 10.05 over 2. It is 5.028 in the clockwise direction. A rectangular coil 40 centimeter long and 32 centimeter wide. Okay, dimensions of the coil 40 centimeter long, 32 centimeter wide. Your attention, please. 32 is the width of the coil. The coil is rotated about an axis parallel to its length, to the length of the coil, in a field of flux density 4 millitesla, with a velocity of 50 meters per second. This is the linear velocity. The coil has 100 turns. We want you to calculate the maximum induced EMF in the coil. Okay, to calculate the instantaneous EMF induced in the coil, when its plane makes an angle 60 with the field. Angle between plane of the coil and field is 60. Okay, if you remember in the problem, linear velocity is given. So we need to obtain angular velocity from this linear velocity. Radius, okay, equals width over 2. Width is equal to 32 centimeters. 32 times 10 power negative 2 over 2. It is 0.16 meter. What is the relation between angular velocity and linear velocity? Angular equals linear over r. So omega equals 50 over 0.16. It is 312.5 rad per second. In this way, we can calculate maximum EMF. It is NAB omega. So 100 number of turns, dimensions 40 and 32 times 10 power negative 4 to convert it from centimeter squared into meter squared. Flux density 4 millitesla, 4 times 10 power negative 3. Angular velocity, we've just obtained it. So maximum is equal to 16 volt. And what about the instantaneous? When the plane makes an angle 60, we'll use cosine 60. Okay, so it is equal to 16. Cosine 60 equals half. So it is 8 volt. Here in front of you, we've got a circuit. The circuit contains 2 batteries, 2 volt battery and 1 volt battery. Okay, and we've got 3 resistors, 1 ohm, 2 ohm, and 4 over 3, okay, ohm resistor. Use Kirchhoff's laws to calculate the value of the current in each resistor. Use Kirchhoff's laws to calculate the value of the current in each resistor. Okay, in front of you, let the current that passes through the circuit of the 2 volt battery is X. Okay, and portion of this current equal to y passes through the 2 ohm resistor. So the portion that passes through the 4/3 ohm resistor is x minus y. Let me say it again. So let x is the current that passes through the 1 ohm resistor. And part of it, part equal to y, passes through 2 ohm resistor. So the other part which passes through the 4/3 ohm resistor is x minus y. Okay? Now, by applying Kirchhoff voltage law, KVL, on loop A, C, B, F, A. A, C, B, F, A. Okay? We can say minus 2y, okay, plus 1. 1 is the EMF of the battery. Yes, minus 1x is equal to 0. This way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.